We are still designing a composite floor. In part 1 of our question, we solved question A, B, as well as C of this question. That is part A, we selected a suitable UB section. Part B, we checked shear capacity. And part C, we checked the headed stud connectors required. In this second part of this question or of this video, we are going to solve part D as well as part E, whereby part D, we are going to check the longitudinal shear capacity of the concrete, and part E, we are going to calculate the imposed load deflection of the beam. Join me so that we solve the next part of this question. I am George Kamiti. So we are in part D of our question, that is longitudinal shear. And in longitudinal shear, we are going first of all to determine the longitudinal force. So we go to longitudinal force, that is V. A longitudinal force V is usually given by NQP divided by S, whereby N is the number of shear connectors in a group, and in every group we have 2 studs. Therefore, N here will be 2. QP, of course, that is the total longitudinal shear force per unit length, and S is the longitudinal spacing center to center of the shear connectors. Therefore, the longitudinal force V will be given by N, which is 2, total number of shear connectors in a group, multiplied by QP, which is 80 kilonewtons. We convert to newtons by multiplying kilonewtons by 1,000, which will be 10 raised to the power of 3, divided by the longitudinal spacing center to center of the groups of shear connectors, and we approximated it to 350 millimeters, though we got 375 millimeters, but 350 looks a bit more safer. Therefore, the longitudinal force V will be equal to 457 newtons per millimeter. After that, we are going to determine the shear failure surface about section AA, as shown in this figure here. The length of failure surface, will be given by 2 times 150 millimeters. Since we have 2 sections AA on the left hand side and on the right hand side, the depth of the concrete flange is 150 millimeters. So on 2 sides, we are going to have 2 times 150, which of course is 300 millimeters. Then the cross-sectional area of the failure surface which is denoted by ACV. Cross-sectional area of the failure surface is going to be 300 times 10 raised to the power of 3. Let me write it down here. So ACV, cross-sectional area of a failure surface, ACV will be equivalent to 300 times 10 raised to the power of 3 millimeters squared per meter. Square millimeters per meter. That's why you are multiplying by 1,000. 10 raised to the power of 3. Then we are going to have a cross-sectional area of reinforcement potential failure surface. Potential failure surface, which is denoted by ASV. And ASV will be given by area of tension stress of the bolt, plus the area of the bolt. And since both areas are the same, the area of the tensile stress area of the bolt and the area of the bolt, both of them are 335 square millimeters. Therefore, this is going to give us 670 square millimeters per meter. That is the value of ASV. Therefore, the shear resistance of concrete shear resistance of concrete which is denoted by VR, will be given by VR is equals 0.7 ASV Fy plus 0.03 times a constant, which is N, multiplied by ACV times FCU, which should be less than or equal to 0.8 multiplied by a constant N multiplied by ACV times the square root of FCU. That is the shear resistance of concrete. ASV, as we have said, that is the cross-sectional area of the failure surface. Fy is the characteristic strength of steel reinforcement, and that is a constant. ACV, cross-sectional area of reinforcement potential failure surface. FCU, characteristic strength of concrete. Therefore, VR will be equal to 0.7 times ASV, which is 670 square millimeters per meter, multiplied by Fy, that is the characteristic strength of reinforcement steel. It is usually 500 newtons per square millimeters. Then we add 0.03 times a constant N, which is 1.0 for normal concrete, multiplied by ACV, which is 300 times 10 raised to the power of 3 millimeters squared per meter. And then we multiply that by FCU, which is characteristic strength of concrete, that is 30. We are going to divide the whole of this calculation by 1,000. The reason being, we have 670 square millimeters per meter. We have 300 times 10 raised to the power of 3 square millimeters per meter. We need to convert square millimeters per meter to square millimeters per millimeter. 1 meter is equivalent to 1,000 millimeters, and therefore 10 raised to the power of 3. This should be less than or equal to 0.8 times a constant N, which is 1.0, times ACV, which is 300 times 10 raised to the power of 3 times the square root of characteristic strength of concrete, which is 30. And therefore, the first part here, when we carry out that calculation, that is going to give us 504.5 newtons per millimeters, which is less than or equal to, the second part is going to give us 1,315 newtons per millimeter. And therefore, we find that that calculation is very much okay, meaning that the section we have selected is all right. It is okay. But in this case, we can also compare V and VR. So we are going to find that the longitudinal shear, which is 457, that is V, is less than the shear resistance of concrete, that is VR, meaning that our section is also okay, and we are good, we are okay, we selected a suitable section. Then from there, we go to shear failure in section BB. So, shear failure in section BB, as shown on this diagram. The shear failure in section BB, we are going first of all to calculate the length of failure surface. Therefore, the length of failure surface will be given by 2 times stud height, 2 times stud height, plus 7 times shank diameter of the stud. And therefore, this is going to be 2 times stud height, which is 100, plus 7 times the diameter of the stud is 19. And this is going to give us 333 millimeters. Then the cross-sectional area of failure surface, that is ACV, is going to be 333 times 10 raised to the power of 3 square millimeters per meter. Square millimeters per meter. Then from there we go to cross-sectional area of reinforcement potential failure surface, that is ASV. And in this case, ASV will be given by twice the area of the bolt. And this is going to be 2 times the area of the bolt, which is 335 square millimeters. And this is going to give us 670 square millimeters per meter. Then we determine the shear resistance of the concrete, that is VR. Therefore, VR will be given by the same formula, 0.7 multiplied by ASV, and in this case ASV is 670 multiplied by characteristic strength of steel reinforcement, which is 500. Then we add these to 0.03 times a constant N for normal concrete, that is 1.0, multiplied by ACV, which is 333. So we multiply that by 333 times 10 raised to the power of 3 square millimeters per meter. Then we multiply by FCU, which is the characteristic strength of concrete, which is 30. Then that calculation should be less than or equal to 0.8 times a constant n, which is 1.0, multiplied by ACV, which is 333 times 10 raised to the power of 3. Then we multiply this by a square root of characteristic strength of concrete, which is 30 newtons per square millimeter. Then we are going to do the following. This part we are going to divide by 1,000, since we have 670 square millimeters per meter. We should convert to square millimeters per millimeter. So we divide by 1,000. Same case to this one, we divide by 1,000 because of 333 square millimeters per meter. So that part should be less than or equal to this. Again, we forgot to do the same here. 10 raised to the power of 3. Divide this part by 1,000, since we have 300 times 10 raised to the power of 3 square millimeters per meter. So VR will now be equal to, the first part is going to give us 534 newtons per millimeter. And the second part is going to give us 1,459 newtons per millimeter. So we find that the first part is less than the second part, meaning that our section is very much okay. And when we compare the shear resistance of the concrete, which is 534 newtons per millimeter, we find that it is greater than the longitudinal force, which is 457 newtons. So it is greater than V, which is 457 newtons per millimeter, meaning that our section is very much okay. Our section is very much all right. So we are done with longitudinal shear. The final part, that is E, is determination or calculation of deflection. So we go to deflection. Now, in deflection, since the beam is simply supported, we are going to use the gross value of the second moment of area, that is IG, of unclacked section to calculate deflection. And in this case, IG, the gross second moment of area, will be given by this formula: IS plus BE ds cubed divided by 12 multiplied by the modular ratio. Then we add these two, A, B, E, ds into D plus ds squared. Then we divide the whole of this part by 4 into A multiplied by the modular ratio plus BE ds. So that is the formula that is going to give us the gross second moment of area. BE is the effective width of our section. ds, of course, is the depth of the concrete flange. This is the modular ratio. The others repeats themselves in that order: B, ds. D is the depth of our selected section. IS in this case is the second moment of area of our steel section, which is obtained from Appendix B of the BS 5950, and it is 12 49,100 centimeters raised to 4. So we convert to millimeters raised to 4. We multiply by 10 raised to the power of 4, since 1 centimeter is equivalent to 10 millimeters. We add this to the effective width of our section. That was 2250 millimeters. We multiply by ds, that is the depth of our section. It is 150 millimeters. So cubed divided by 12 times the modular ratio for normal concrete is usually 10. Then we add these to the area of our section that is obtained from Appendix B of the BS 5950. It is 57 square millimeters. Then we multiply this by a BE, that is the effective width of our section, which is 2250. Then we multiply by the depth of our section, which is 150 millimeters, into D, that is the depth of the flange obtained from Appendix B, that is 352 millimeters. Then we add DS, the depth of our section, 150. Then we square that. We divide the whole of that part by 4 into the area of our section from Appendix B, 57 square centimeters, convert to square millimeters, multiply by 10 squared, times modular ratio for normal concrete, which is 10. Then we add BE, the effective width of our section, that is 2250, times the depth of our section, depth of the concrete flange or concrete slab, 150. So when we carry out the whole of this calculation, it is going to give us IG, which is 49,150 times 10 raised to the power of 4 millimeters raised to 4. So from there, we can now be able to calculate the deflection at the midspan. Therefore, deflection at the center of our beam will be given by 5 WL raised to the power of 4 divided by 384 EI. And in this case, we are going to have 5 times this W will be given by the total imposed load or total live rods. Total live rods, we have 4 kilonewtons of total live rod. We have 4 kilonewtons of imposed load plus 1 kilonewton per square meter of partitions, which is 5 kilonewtons per square meter. Therefore, W will be given by 5 multiplied by the span, which is 3.5 meters. Then we multiply this by 9, which is the beam span raised to the power of 4. Then we multiply by 10 raised to the power of 12. Why raised to the power of 12? Because we need to convert kilonewton per square meter to newtons per square millimeter. We need to convert 3.5 meters to millimeters. We need to convert 9 meters to millimeters. So we are multiplying by 10 raised to the power of 12. That is a million times another million. Then we divide this by 384 multiplied by the Young's modulus of elasticity of steel is usually 205 kilonewtons per square millimeter. So we are going to convert this 205 kilonewtons to newtons per square millimeter by multiplying it by 1,000. Then we multiply by I, which is the IG, the gross second moment of area that we have obtained here. That is 49,150 times 10 raised to the power of 4. And when we carry out that calculation, it is going to give us 14.8 millimeters. This should be less than L, the span of the beam section, divided by 360. That is for beam carrying plaster or any other brittle finish. L in this case is 9 meters converted to millimeters. That is 9,000 millimeters. We divide by 360, which is 25 millimeters. Therefore, we find that the deflection, which is 14.8 millimeters, is less than L over 360, which is 9,000 over 360, which is 25 millimeters, meaning that the section we have selected is very much okay. We can conclude by saying, therefore, adopt 356 by 171 by 45 UB section in grade S355 steel. So that is our conclusion, and we have found that our section 356 by 171 by 45 is suitable in all situations and in all cases that we have tested it. So, ladies and gentlemen, we are done with our today's calculation. Thank you for following up to this point, up to the end. And we appreciate for your support. Please, if you are not yet subscribed to our channel, please consider hitting that subscription button, and we are going to appreciate so very much. Let's meet in yet another lesson. Thank you.